Okay. Hi, I'm Ishan, and this is.
Hi, I'm Evan, and our group is part of MAM, but we worked on a separate aim on a different model and a different task overall. And I'll hand it to Ishan to start us off.
Yeah, awesome. So the question that we sort of started off with the rest of our group was taking micro language models and trying to fine tune them for specific tasks, and that was what seeded the entire project that we worked on this quarter. So the idea is essentially to take a small micro language model and fine tune it to be better at math, but selecting that small language model was sort of its own task. Throughout the quarter, sort of like halfway in between, a model came out called HRM Text. This model was state of the art, extremely sample efficient, very, very good. And it kind of struck us by surprise, but it was an exciting opportunity for us to sort of fine tune a model that was brand new, state of the art, and extremely performant. So the way that HRM text works, as opposed to a vanilla transformer per se, is that HRM text is a recurrent language model, meaning that it has two layers of transformers, and these two transformers work together, passing between them the logics that are then used and processed, and then eventually outputting some sort of distribution that's supposedly more accurate because there's better thinking involved. The sample efficiency was crazy. We can show sort of a graph of that in a second, but the comparative models, for example, the Quen models that the other group showed, were trained on 100 trillion tokens. This model was trained on 40 billion tokens in less than 2 days on 8 H100s, which is ridiculous. The models it's comparing itself against are multi-million-dollar training runs. This is a $1,600 training run, and it outperforms the Quen series and every other series in its weight class by 10 to 20% on any significant benchmark. So it's crazy. Was very exciting. And there's lots of interesting architecture, but we don't need to go into the nuances right now. Now, why reinforcement learning? So SFT is good for introducing a model in terms of shifting its distribution, in terms of giving certain behavior that you want. Like, for example, if you want it to output in a specific format, this is a good idea for SFT. Reinforcement learning is better in a lot of ways, but it's better specifically for our case in terms of improving math because the model was already capable of doing a lot of the math that we wanted it to do. So we specifically took a benchmark that involved pre-calculus, algebra, combinatorics, geometry, and some other categories. And the goal of reinforcement learning was to then take the success rate of the model, which was maybe if you ran it 32 times on the same problem, it'd succeed like twice, and increase that so that when we do it at just a one rollout per problem, we can increase the likelihood that this benchmark run is successful on more problems, especially the difficult ones. So in the end, we selected DAPO as the approach that we took. It's a modification on GRPO. How many people are familiar with GRPO? Should I go over it a little bit? The idea of GRPO is relatively simple. It's just basically to create a group of responses. Because if you can imagine, if you try the same problem 16 times, hopefully the model is more likely to solve it than if you tried just once. Now the idea is if we can get some of those times the model to be correct and some of them to not be correct, then we can sort of have some interesting signal where we push it in the direction of the correct weights or the weights where it got this correct and push it away from the ones where it got it incorrect. And that's the idea behind GRPO. DAPO is a slight modification on top of this, mainly because GRPO sometimes has an issue where there are dead rollouts. Essentially, the model gets it correct every single time or it gets it wrong every single time. And this isn't ideal. It makes it such that there's no advantage. We don't really need to go into the nuances of GRPO right now, but essentially you can imagine that DAPO is just a slight modification on top of this that makes it better for our use case.
Yeah, another thing to talk about is the data that we use because HRM text is unique in that it uses instruction pairs as its pre-training rather than just wiki text, which is what a lot of models use. Instead of just like looking at all the ton of data like on the internet and just memorizing it, it has a format where it has an instruction and then a response. And so when we do supervised fine tuning or when we do reinforcement learning, although reinforcement learning is always based off of instruction response, we have to format in the same sort of way. And especially for math, it's important that we have the right sort of format in our answers in order so that reinforcement learning works well. Because our reward formula that we give for the model might be based off of formatting. And if the model doesn't know which part of its answer is like its answer to the math problem, then it might get stuff wrong that it's not supposed to get wrong. It might get stuff that's right just because it doesn't know how to format things and compare it to the ground truth answer. So here's the details about the data that we used. So open R1 math and the math training set for SFT. Those are the sizes. And then for DAPO, we are trying to bias the model towards harder problems, which is why from the math training set, we took levels 3 through 5. There's 5 levels of math problems, and we took the harder 3 levels, along with Open R1 and DAPO math, which are just some other math sets, and especially tailored towards DRPO specifically. And so with a mixture of these data sets used for our DAPO training, we were able to get the results that we did. There's a couple notes. First, like we were considering about adding in general instructions in order to avoid catastrophic forgetting, since this HRM text model is actually not a general transformer model. It uses a sort of recurrent network where there's like 3 low modules, 1 high module, so you can read the paper. But it suffers from a lot of forgetting if you train it for too long or if you give it too much data. And so the SFT has to be very finely tuned. The data sets have to be very finely tuned in order for it to not crash and burn and lose all of its general knowledge that it gained during pre-training. So this was a big struggle, trying to find the right data to use for our training methods. Here are our hyperparameters. For supervised fine tuning, we use LoRa, rank 16 adapters. And for 1 epoch, because if you train it for longer, it might crash and forget the stuff that it learned in pre-training. The precision, the targets, and the DAPO stuff as well. There's 2 things that we didn't really cover, things about clipping, and the objective and the generation. Those are all the hyperparameters that we used inside of our training methods. And the hardware is down at the bottom. We just use an H200 for most of these things. All right, so what went wrong? There's a couple things. First off, we had some token cap issues. We were looking at our first rollouts, and because the model's answers were truncated, the way that math problems work is that it generates this really long chain of reasoning, and at the end it has its answer in like a box format. But if you put the token cap too low, then it doesn't get to the answer, and so it marks the answer wrong even though it would have gotten it right if you just gave it enough time. So there's one answer. Second is the box format, which is why we did SFT, or motivation for it, so that it would consistently list its answers in this sort of /box format, because sometimes, depending on the data that you use, it will do like an answer and then colon and then a whole lot of explanation, and then just in natural language will say like this is the answer. So it's really hard to parse the answer from that. 2 other things is TRL and VLLM. These are like model serving platforms. Because HRM is such a new architecture, it's not compatible with these 2, just without adapters, specifically because of an attention mask that it uses called prefix LM, where it has full attention on the instruction, so you can kind of cheat for the entire instruction, but for the response, it's causal attention. So it doesn't allow the model to look at the entire thing, it only looked at the previous tokens. And so that's not compatible with either VLM or TRL, so we had to use Hugging Face Generate, which is a more general model architecture serving platform. Going finally to our results, you can see here from these heat maps, these are the 3 different models that we tried, so base, supervised fine tuning, and DAPO from left to right. You can see the maps of the different types of problems that they're able to solve. It's stratified across the models and also the types of problems that they were, like algebra, accounting and probability, etc. And you can see at the very bottom right corner, it's very red because those are the level 5 problems on the very right corner. And it seems like pre-calculus is very hard for these models. So you can see generally that they look about the same, that they fail on the right things, on about the same things, but we can see that specifically for DAPO, that over in this bottom right corner, things are a little less red in this box. There's some shifting around here. There's a little bit of noise in like what it gets right and what it gets wrong, but generally the graph is a little greener, and that's reflected through the numbers of the general accuracy. You can see from base and SFT are about the same, and then DAPO has like a slight 2.3 advantage over base, and that's just with 80 steps over DAPO. We could have run this a lot longer, but it does take a while. Yeah.
Yeah, and so I guess in terms of results and things that are interesting, one of the coolest things is that DAPO seems to improve performance on the most difficult problems, which is what we were hoping for, but it's cool to confirm that, because I mean, it could degrade performance on the easier problems at the cost of, or as a cost of improving performance on the harder ones, but it's nice to see some continuity where it improves performance overall. It was interesting to see that SFT didn't really contribute anything. And so as a result, that would be a next step for us, is to look at why SFT didn't seem to really improve the pass rate that much, and to try to understand if maybe we should modify things in order to improve things at that point. There's a lot more learnings to happen in terms of the plumbing. They did a lot of custom and bespoke things that we would kind of want to look at more closely to understand why these choices were made. Like, they wrote a custom kernel for certain parts of it. They had adapters in place for certain parts of it. We could only run this on hoppers because they use flash attention 3. So there's a lot of situations where understanding the design decisions they made within their code would be useful. Yeah, and in terms of where we'd go next, it'd probably be extensions on DAPO. Try to run DAPO with more steps involved and with a larger data set. And then one other thing that I think is interesting is we did all of this with LoRa adapters. I was looking at the forums where a lot of people are tinkering with this model for fine-tuning right now. It seems like everybody's doing full fine-tuning and that LoRa hasn't really been that effective. So that'd also probably be an immediate next step, is to go straight to full fine-tuning and avoid LoRa altogether. Yeah, cool. So I think that was kind of everything. Thank you.
Yeah. That's all we have. Yeah. Yeah, we're open to any questions now.
I think that one of the questions I had is, you made a conclusion that it was mostly useful for frontier questions, harder questions. How did you come to that conclusion? I didn't see any examples.
Yeah, so that was our initial goal with the training data that we used for DAPO. As I said earlier, we used level 3 and level 5 problems from this test set, and also the DAPO problems and the other data set that we mixed in were harder than the ones that we tried SFT on and the ones that they did pre-training on. And that's reflected through the heat map. It's not like super obvious because the difference is a little small. The colors don't change super drastically, but basically what it did is it increased the pass rate for those harder level 5 and level 4 problems while maintaining about the same pass rate for the 1 through 3 problems. So if you look at like the heat maps and all the data that we have for the results that we have, that's the result that ended up happening. Yeah.
Did you see what was failing and what reinforcement learning helped? Like, if we looked at the reasoning traces of what, does this have reasoning or?
Yeah, it's supposed to generate like a reasoning trace and then a boxed output.
Did you guys look at that to see like what started working suddenly once with reinforcement learning?
Yeah, I did look through some of the reasoning traces for the ones that it failed and the ones that it succeeded on. I mean, they're math problems, so like the correct answer will always like have sort of like a similar like reasoning trace in order to get to the right answer. And I couldn't find like a really strong pattern to show like why reinforcement learning made the difference, especially because the difference, it was like 800 sets we used for, or 800 problems we used for eval harness. And so the difference you see in the graph is like about like 10 problems that reinforcement learning model got better than the SFT or the base. And so based off of 10 problems, it's kind of like hard to see if there's a pattern or not. It kind of just looks like the reasoning went the right way. But I think it's significant enough to at least say it's not noise.
Yeah. And also fundamentally that is sort of what DAPO is about, right? It's just about taking like best of n and increasing the likelihood. Or so instead of 2 out of 16, you get 8 out of 16. I don't know that there's a common thread. There's random ways that the model thinks and then gets the right answer. And honestly, our signal is also very just binary. It's either it got it right or it got it wrong. So it's also a bit hard to train the model to have a better way of thinking, especially with so few samples. Like, we'd probably need to expand it to start establishing a common thread.
Last question, why did you go after math? Seems like small models are not going to be good at math anyway. And from an application perspective, it doesn't make sense to go after math.
Yeah, so I think a couple of reasons. There aren't many domains that are verifiable in the way that math is. So that was one of the most convenient. The second was they had already posted a result for a math benchmark, so that made it very convenient as well. And I think the third is there's a lot of data and a lot of research in the math domain specifically, so that we could, like, there was an entire data set that we could use. We didn't have to generate our own data because of that. So, yeah, and so that was the main reason we selected math. I guess the alternative that was maybe immediately coming to mind is tool use, and that's probably the other one. And tool use, frankly, I have more background in math as well. That's why we did that.
Yeah, adding on to what Ishan said, there's a lot of work in RLVR, like with reinforcement learning with verifiable rewards. So like the sparse rewards thing is not like super a problem. That's what people are trying to work on. Also, you can look at these benchmarks for drop, ArcC, MMLU, these reasoning tasks. I guess like MMLU, it's also like a reasoning thing, but this one is at 56, and that's like a big difference from 82 and 81. So we thought that there would be more headroom for the model to like grow on this benchmark, whereas the other ones were sort of already saturated, like we didn't know how much of a difference it would make to have RL. I don't know. We thought there was enough signal in math to do some significant work. So that's why we chose math.